All right, welcome back to Mr. P Helps with Algebra. This is Unit 4, Topic 3, Lesson number 3. We're going to be, once again, exploring the relationships between linear equations and quadratic equations. We're going to start off with a warm-up about the fundamental theorem of arithmetic. So we're going to be looking at prime factorization. So we're going to change this prime factorization into standard whole numbers. 2 to the 4th power is 2, 4, 8, 16. Multiply that by 3 to the first power, which is 3. Multiply that by 5 to the second power, which is 25. So then you're going to want to use your calculator and figure out what that is. So that's 16 times 3 times 25, which is going to give you 1,200. So for the next one, 3 times 3 is 9, times 3 is 27, times 3 again is 81. 5 to the second power is 25. And 7 to the second power is 49. So once again, multiply those numbers. 49 times 25 times 81. And you're going to get 99,225. 5 to the second power is 25. 11 to the second power is 121. And 13 to the first power is 13. 121 times 13 times 25 gives me 39,325. Now it says the following problems are factorizations of expressions called quadratics. Given the factors, multiply to find the quadratic expression, add the like terms, and then write them in the x squared term. Alright, so we're going to use FOIL method, which we did on the last warm-up. So x times x is x squared. Outsides gives me negative 7x. Insides, 5 times x is 5x. On the last, 5 times negative 7 is negative 35. So now we can combine the middle two terms. Negative 7x plus 5x is negative 2x, because they have the exact same variable with the exact same exponent, and bring the other two terms down because they are not the same. Okay, so I'm going to erase that out. Next question. So first is x squared. Outers is 3x. Inners is 8x. They're on the inside. And then last is 24. Add the two terms on the inside again, and you get 11x. And bring your other two terms down, and there's your answer. Last question. So this question is a little bit different because we've got a binomial times a binomial with a monomial on the outside. So I'm going to leave that 2 on the outside. I could multiply it first and use the distributive property, but I'm going to decide to do it last. So I'm going to make parentheses here and put whatever this binomial times this binomial is in this parenthesis. So that's going to give me x squared minus 4x minus 9 more x's plus 36. What I could then do is then multiply it by 2, but instead I'm going to combine like terms first. Negative 4 minus 9 more. So that's x squared minus 13x plus 36. And then multiply everything by 2, and you get 2x squared minus 26x plus 72. All right, so as I mentioned earlier, so this lesson is going to, once again, it's a third lesson. We're going to explore relationships of quadratic patterns to linear patterns. So if each of these, so Scott wants to do some push-ups, and each one of these blocks represents one push-up. So when you look at the blocks from day 1, day 2, day 3, day 4, it looks pretty obviously, you see the pattern that it's adding 2 blocks each day. So that would be a linear pattern because that's a common difference. It goes from 3 blocks to 5 blocks to 7 to 9. So that's definitely a linear pattern. But then we're going to talk about, we're also going to write an equation for, well, what if we combine those and find the total of all the push-ups that he's done all together? So let's do the linear one first. So we're going to talk recursive and explicit formulas. Is basically, that's the goal for this lesson. The recursive formula, I want to give a starting point, so I would say f of 1 is 3 push-ups. F of n is equal to f of n minus 1, which represents the amount of push-ups in the previous day, and you're adding 2 to it because that's the common difference. For the explicit formula, so you would say y equals, or f of n equals, doesn't matter, y equals the pattern times x, so that's 2 times x, and plus the 0th term, which would have been 1 block if we had gone to the 0th day. So decreasing by 2 blocks, this would have been 1 block right there. Or you can just say, well, 2 times any x, 2 times 1 is 2, plus 1 would be 3. And that works for any single pattern. So if I want to figure out how many push-ups you do on the 100th day, that'd be 201, because 2 times 100 plus 1 gives you that answer. All right, so then I'm going to put that into a table format. So we've got 3, 5, 7, 9, 11, and so forth. And then once again, as I mentioned earlier, I'm going to now take that linear pattern and turn it into a quadratic pattern by adding them, finding the total number of push-ups. Goes from 3 to 8 to 15 to 24 to 35. And then what I'm going to do is I'm going to find the differences between those two terms. This happens to be plus 5, then plus 7, plus 9, plus 11. And then find the differences of those differences. And you're going to notice that these differences all have a common difference. We call that a second difference of plus 2. All quadratic patterns have a second difference. That is the same thing, a common second difference. So now we've already talked about the linear and exponential equations for the linear. So I'm going to do that same thing for the quadratic. So the explicit and the recursive. I'm going to start with the recursive because I know I ignored it on the last video. The starting point, f of 1 equals 3, the previous term. Okay, so I'm going to really break this down a little bit. The way you find the recursive formula of a quadratic function is to take the differences and compare it to a linearly to the x terms. So you're only looking at those two. Now keep in mind that I'm ignoring this column because that was the linear data. So really I have 4 pieces of data. I have the x's, the y's, the first differences, and the second differences. Now let's compare this to their first difference. If I multiply, well, this is plus 2. So it's going to be the previous term plus 2x. And the reason why I know it's 2x because that is the second difference. This will always be the second difference. Now, if I multiply x times 2, 2 times 2 is 4. What would I have to do to 4 to make it 5? Add 1 to it. And you're going to notice that that always works. 2 times 3 makes 6 plus 1 is 7. So you're adding 7 to the second term. Okay, so that's the recursive. Now I'm going to talk about the explicit. And this one's going to be a little tricky because I can't just take those blocks, and if I actually had the physical blocks, I can maybe make rectangles out of them using like algebra tiles. But since I can't actually do that, you're just going to have to trust me that it happens to be n times n plus 2. And I know you're thinking, well, the n plus 2 is probably the same thing as the common difference, okay? I don't know for sure if that's exactly the reason why it's working out that way, but that is what it is, or x times x plus 2. So let's assume I used x's because I have to use x's for the explicit formula. So y equals, I could either write x times x plus 2, or I could use the distributive property and say that's x squared plus 2x. Now let me prove that that works. 1 times itself is 1, plus 2 times 1, which is 2. 1 plus 2 makes 3. It works. 2 times 2 is 4. 4 plus 2 times 2 again is another 4, makes 8. One last one. 3 times 3 is 9. That's times itself. Plus 2 times 3 is 6. 9 plus 6 makes 15. So there, I've tested it 3 times, so now you can see that it works for every single one of the equations. All right, so last but not least, talking about the homework. So we're looking at these patterns, and just like we just did a second ago, we want to determine what kind of function is it, and then write the recursive equation. So all we need to do, well, first I noticed that all the x's are in a common difference. They all are increasing by 1. Then I look at the y columns, and I notice, well, this number is increasing by 5, and then by 6, and then it looks like it's increasing by 7, and, oh, nope. That was 6, sorry, let me go back. Okay, so this one was 6. This one was also 6. This one was also 6. Okay, so that makes a big difference because that means that this is a linear pattern. So the recursive formula, f of negative 3 equals negative 23. So that's my starting point. You can use any point you want. F of any number is equal to the previous number plus 6. Okay, so I look at the next one, 4, 0, negative 2. That decreased by 4, then it decreased by 2, then it stayed the same. And then it increased by 2. Okay, so now we have a second difference this time. The differences are increasing by 2, which tells me that this is a quadratic equation. First, I want to give my starting point. F of negative 3 is 4. F of n is equal to the previous number. And then like I mentioned before, so when you have a quadratic, you're looking at the third column and comparing it to the first column. So you're looking at the differences and compare it to the x's and finding that linear relationship. So plus 2x, because that was the second difference. 2 times this x would be -4, and what would I have to do to -4 to make it -2? And that would be add 2. So it looks like it's previous term plus 2x plus 2. All right, last one. -15 goes to -10, so that looks like, all right, what is this, half? No, it's not, so that's add 5, add 5, add 5. Okay, so that makes this linear. So f of -3 equals -15. Any number is found by taking its previous number and adding 5 to it, because it was linear. All right, and last question. Predict the number of squares in figure 30. So I'm looking at this, and I want to find, I'm not going to continue this pattern and make that symbol 30 times. That would take me way too long. So I'm going to find the equation by counting the blocks. 1, 2, 3, 4, 5. So it goes from 5 blocks. 1, 2, 3, 4, 8 to 10 blocks. 1, 2, 3, 4, 5, 15, 17 blocks. So it looks like it went from +5 to +7. So that's, and then it's going to go to +9, which would make this 26 blocks. So this is a quadratic equation. It does have a second difference in this case, a second difference of +2. All right, so then I need to find that equation so I can model it. So if it goes +5, +7, +9, I could continue to go +11, +13, +15, +17, but I would need to do that 27 more times, and that is very time consuming. So the easier way would be to find that equation. The issue here is the recursive formula would be very easy. The explicit formula, x squared, so 1 squared plus 3x. See if that works for all of the terms. 2 plus 6. Okay, it seems to me I'm going to have to make another video because I was not prepared with this equation. You're going to need a graphic calculator, which I do not have on hand at the very moment, and plug the data in and then figure it out. Actually, I'll take that back. We'll make this one video. Thank you very much. Battery's low. Hopefully it's going to hold out. 1, 2, 3. And we had 5, 10. So once again, so if you are holding a graphic calculator, basically I press stat for statistics. I went to one edit and I'm putting it in as a table. 1, 2, 3, 5, 10, 26. And then you go to stat, calculate number 5 for quadratic regression. And it's telling me, oh, no way I would have ever guessed that. 5.5x squared minus 11.5x plus 11. Okay, so if I'm going to put x is 30, so that's 5.5 times 30 times 30. That gives me 4950 for right here. This is a pretty crazy question. Minus 11.5 times 30 is minus 345 plus 11. All right, so add that to the 4950 and then add that to 11. Gives me an answer of 4,616 blocks. All right, thank you for being patient with me. I know I went to 13 minutes. Please give it a like to help you learn something and subscribe if you haven't done so already. Thank you. Have a wonderful day.